And what we're going to take advantage of is that with similar triangles, the ratio of the side lengths here is exactly the same. So that means that if I take delta V, so the short side length here, the change in the velocity over the long side length, V, I'm going to call it V now because V1 and V2 are the same. That means that the ratio of the short side to the long side on this triangle is exactly equal to the ratio of the short side to the long side on this triangle. And that is just a property of similar triangles. So that means short side is delta R over one of the long sides, doesn't matter which one we choose. Let's just call it R since they're congruent. Now, earlier up here, we recognized that, well, delta R is really just the displacement, which we've used before as delta X. So I'm going to replace delta R here with delta X. Well, this object is moving at a constant speed. So in kinematics previously, we have learned that if you want to know the displacement of an object, delta X, the displacement of an object is just calculated as the speed at which the object is moving, or the velocity, the magnitude of the velocity, times the amount of time that it's moving for. If we do a little bit of dimensional analysis on this, right, this is our speed, or our velocity is the meters per second that something is moving, and then the time is just the seconds. Right, when I multiply these together, seconds cancel out, so I get that distance, that displacement, meters here. So displacement can just be calculated as the velocity times the time. So I'm going to do a substitution where I'm going to substitute delta X in my equation above here with velocity times time, since that's just another way to express my displacement. So now this equation, just going to move it over here, looks like delta V, change in velocity over velocity, is equal to velocity times time, that was my substitution, over the radius still. All right, we're getting close to the end here. So all I'm going to do from this point is a little bit of algebraic rearrangement. And you'll see why in a moment here. So the first step is that I'm going to move this velocity that's in the denominator over to the other side. So since this velocity is dividing delta V, I'm going to multiply both sides by V. That means that here it will cancel out, make 1. And overall this becomes delta V is equal to, so V times V gives me V squared times time over R. And then last step is that I want to move this time variable over to the other side. So since it's multiplying this side, I'm going to divide by T on both sides. And my final expression, since the T's are going to cancel out, becomes delta V over time is equal to V squared over R. Now, what is the change in the velocity over time? What variable do we find as how the velocity is changing every second? That sounds a lot like acceleration. So this is indeed that centripetal acceleration. We can quantify the acceleration, how much the velocity is really changing by, even though it's just changing its direction. Delta V over T is acceleration, right? That is the definition of acceleration. So really, the centripetal acceleration can be given by this expression here. That centripetal acceleration is the velocity squared divided by the radius of the turn. Now, intuitively, this actually kind of makes a little bit of sense because you have to accelerate more as you're turning. So you're creating more G's, or you need more amount of force, let's say, in order to make this turn. If you're moving faster, so think about in your car trying to take a turn at a fast speed. So the velocity, the speed at which you're turning, really affects that acceleration. And then the other thing that affects it is the radius. So radius being how tight is the turn. So if you have a really small radius, you're dividing by a small number, that makes your acceleration really large. Or if you make that radius larger, if you take a wider turn, then you don't have to accelerate as much as you're turning. So this is actually a new equation for us about how we can quantify the centripetal acceleration that an object experiences as it's turning. Now we just need to add one more little equation to this, which is that if this is the centripetal acceleration, we want to add an equation for centripetal force. So from the previous page, we have that centripetal acceleration can be quantified as the velocity squared divided by the radius. We just want to define an equation for the centripetal force now. Now, from previous readings or the previous lecture, we noted that centripetal force, which I'm going to note as Fc, that's really just the net force. So it's the F net in the radial direction, so pointing inwards or outwards from that circle. And F net from before we've realized is equal to the mass of the object times its acceleration. Or the way that we've really written this is that the acceleration that an object has to experience is the net force divided by the mass. So centripetal acceleration is really just when I multiply by mass to my v squared over r equation. So Fc is just going to be mass times centripetal acceleration, or really mass times the velocity squared divided by the radius. So this Fc is equal to mass times velocity squared over radius is the equation for centripetal force. Now, let's do a couple of examples for how we'd actually use this equation in some problems to quantify maybe the friction between your tires and the road when you're making a turn, or this is useful to figure out like how many G's does somebody experience when they're on a roller coaster, etc. So let's say we're asked to figure out how much friction is required between a car's tires and the road in order to take a turn at 30 miles per hour with a radius of 10 meters. Little bit of a funny question because we're mixing units here, some imperial miles per hour and then 10 meters. Anytime you're given something in those imperial units, we should convert them into the metric. But let's make a little bit of a game plan for this. I would say always the first thing to do is draw your free body diagram. Now let's define that for simplicity, that this thing is coasting around the turn. So he's not really applying the accelerator and also not braking. So in that case, for a free body diagram, if we're looking at the car turning on this flat road, and really I should have defined that it's flat here. In order for them to be turning, they need some amount of inward force, and as we talked about before, that force that's causing the turn is really just the friction between the car's tires and the road. So our free body diagram would just look something like this, with an equal normal and gravitational force, and then the friction pointing inwards. So start with your free body diagram. That allows us to see that the centripetal force here is really just the friction force. We don't have to deal with adding and subtracting two forces. We just have the friction force. So the second step is really to write your expression for Fc, for the centripetal force. So for us, that's Fc is just equal to the friction. And then the third step here is to then use, I'm going to call it the Fc equals M. Oh, cat. Okay. mv squared over r equation to answer the problem. Oh, we're going to get another cat appearance. Okay, so in this case, if I want to actually quantify the friction, I know that since Fc is equal to Ff, I can just say Ff has to be equal to mass of the car times v squared over r. Just realize that I didn't give you the mass of the car, so let's add that in here, that the mass is going to be equal to 1,200 kilograms. We need to know the velocity has to be in our standard units, so we need to convert miles per hour into meters per second, and then we need to know the radius. So do a quick work or exercise in dimensional analysis. So we know we need to know the velocity. It's given to us in 30 miles per hour. Do some conversions. I know that 1 hour is 3,600 seconds, so I've gotten rid of my hours, and let's just use that there's about 1,600 meters in 1 mile. So that means they're going 13.3 meters per second or so. And then from there, we're just going to plug in all of our knowns. So the mass, the velocity, and the radius, and calculate. And it's a really large number. So 21,333 newtons or so. This is probably impossible, but who knows? This is a really short radius, so it's kind of looking at if you're taking a super, super sharp turn. That's a pretty large amount of friction that would be necessary. So in this case, probably your car isn't going to have that much friction between its tires and the road, unless the road has been like stuck with tar or something that makes it extra sticky. So in this case, probably you don't have that much friction between your tires and the road, and you probably would actually, continue moving in a straight line, and you would end up off the road in this case, or skidding. Okay, I'm gonna let you do one more example. We're just gonna do a second example where you can try it on your own, using like a spinning yo-yo. All right, so a person is whirling a yo-yo in a vertical circle. I want you to determine the amount of tension in the string at the bottom of the loop when the yo-yo is moving at 5 meters per second. The length of the string is 0.75 meters, and the yo-yo has a mass of 125 grams. Now, let me just draw this picture for you. So you have the yo-yo at the bottom of its loop. It's turning in a circle this way. So here's the center of the circle. The length of the string is approximately the radius. That's what we're going to use. So here's that radius. And then we know that it has this velocity of 5 meters per second. So I want you to try to complete this problem on your own here. Pause the video and spend some time working through it, and then I'll work through the solution in a moment.
All right, well, it turns out that my videos are way too long, so I'm going to post the solution to that practice problem as another video. But I'm going to say bye from here. I hope that these examples are going to help you here, and there will be a practice worksheet tomorrow related to lots of these types of problems for you to work on. Okay, see you later. Bye.